Everybody now to talk on low-dimensional quantum magnets, and I will do both. Talk a bit about new phases, dynamics, and introduce a bit of comparison with between experiments and theory, which we have done really extensively in that field in the last few years. And then the Terry will follow up on the topic and go deeper in some of the more computational and theory work we do together and some other projects. So I think this is a bit the start here. I think most of the audience is very interested to find exciting model situations where we can simulate quantum systems, quantum many-body systems, which are controllable, and eventually do experimental work and compare that with theory. And some examples you have heard this last session. It can be do measure transport both with electrons, but also with cold atoms. Another example you can see here, this is basically more or less a multi-insulator transition. On the left, you would see the famous example from cold atom. In the middle, you would see the theory. And on the right, you would see some experimental work on quantum magnets. And so this specific data is about Higgs excitations. And they were also then seen in the same transitions done with cold atoms. So this is very exciting. And what we want to do, of course, is at the end to have a very good model system in a sense that we can understand the Hamiltonian, then eventually do computational work, theory, and be able to quantitatively compare what we calculate and what we measure. And that's usually where there's a lot of insight. And I believe that for quantum magnets, this has been a very successful field in the last few years. We certainly have a very high level of controllability. Maybe it's not as high and as complex as for the cold atoms, but it's also very good. We can apply pressure to the field. And what is most important is the experimental techniques we have been established for years. You know, many of the techniques produce very quantitative results. So something we can have neutron scattering cross sections known on absolute units. And that makes it very easy to compare. There's no free parameter. The prefactors can be known for scaling plots and stuff like that. So I will now go a bit deeper on that. And obviously there's been a lot of progress in all of these areas. I mean, this is obvious. That's a big computer. That's the biggest one we have in Switzerland, with state of the National Supercomputing Center. And of course, that was a prerequisite in the last years to just make bigger machines, bigger calculation QMC, allowing exact organization with larger system. And I'm sure you have seen beautiful examples already during the talks. And later on, Thierry will give you further examples with DMRG. But I'm here to present the experiments, and also there has been really quite some progress recently. And one big one is in neutron spectroscopy. I'm sure that Steve Nagler has shown beautiful examples yesterday about his Kitaev work, which unfortunately I couldn't attend. But there the breakthrough really, to some extent in our field, was to these time-of-flight spectrometers. You see an example here. There are big machines, big detectors. You see a man there next to the detector system. These detectors can have 40,000 pixels. Each of them can measure an energy spectrum. And basically these machines now allow us to measure the full dynamics of a system. As long as the neutron couples to the excitations or the correlations in the system, you can see all of it everywhere in Q space. How the experiments are done is then you often see now these maps. You would not see a 2D plot of data. Very often we show now fancy contour plots of data. And that's simply because that's essentially a 4-dimensional unit you measure. And what you see here is just an example for this. The two axes are just two Q directions in a crystal. And then the white and the green area is where the detector is sensitive. And in the background, we see the structure factor plotted. You would then put your crystal, you would typically spin it. The detector would also have even an out-of-plane direction. And after spinning it for a while, you essentially get the full 4-dimensional information, 3 Q directions, 1 energy axis at the same time. And that allows us really to go very deep in data analysis, particularly for systems now where the signals are quite complex. A good example was continuum of some sort, measured in Kitaev systems or 1-dimensional systems and so on. So this is a big breakthrough. There are many machines of this type now. This is a picture of the spallation neutron source SNES in the US. That's a project in Europe, the European spallation source, where we'll build more of these machines. So there's, there are these machines already available, and they do very powerful, produce very powerful data. And now we will get more of those, and that would be very exciting to measure this. At the Paul Scherrer Institute, where I work most of the time, we do have many of these experimental probes, not only neutrons, we also do photons, muons. We also have a spallation source, but it has a different time structure. There we focus more in doing experiments now under multi-extreme conditions. I mentioned the tunability of condensed matter systems. They're actually quite high. We can apply high magnetic fields, high pressures, control the atomic distances, exchange parameters in the systems. And I think the strontium copper borate, Shasky Sutherland work presented also yesterday is a very good example of that. That needs a different type of spectrometers, which we also optimize over time. You see an example here. It's a so-called multiplexing machine. It basically does a different thing to what I've just told you before. It's not only measuring the full Q and energy space, it also allows you to do that under extreme conditions, but that usually restricts the phase space you can see in the scattering experiment. So that's a spectrometer which we just completed recently, which basically is optimized for such a situation. It allows us to apply pressure cells and still analyze energies at 8 different levels of the scattered neutrons. So we're continuously pushing, the boundaries of the experiments to basically get better information on smaller crystals under more extreme conditions. And a lot is be done right now, both on the source side and the spectrometer side. The biggest renewal, let's say a new thing now we have right now at the Institute is called free electron laser. There's of course LCLS so in the US, and we have the European XFEL now. And what it does is essentially, and it's not so much applied yet to quantum magnets, but we're working on it, and I will say something towards the end. And so the time structure of the X-ray pulses generated here on the femtosecond range, and we essentially, eventually when you have the cross-section with soft X-rays, we hope to see then also the real-time evolution of phenomena in quantum magnets and for correlated systems. And there is really a lot to be discovered there. I mean, if you think about everything we do and talk about today about quantum many-body systems, if you do that now in time-dependent Hamiltonian, you would agree with me that this is quite a challenge for both for the experimental side and also for computational work. And that's why we are very excited about these possibilities. That's how it looks. It's 750 meters, and I can just run you quickly along the tunnel and you can see how it looks inside. So if you start from the ion source, you go along 750 meters, the electrons, you do in bunches. The process you use is self as, I probably got to talk at the same time. So you could maybe ask yourself, I mean, if you could do everything on a computer, it probably would not be worth to spend so much money and effort on building such a machine. But of course, that's not true. So we should always push each other. I see it's very much like that, doing experiments and pushing calculations further. And I believe what has happened in quantum magnets was very much like this in the last few years. So this was a bit my introduction. I will go now into 2 specific examples. One will be about 1D. And also mention a bit disorder in this context in a class of metal organic materials. And then Jerry will follow up on this. And the second will be an example on 2D. In both of these cases, the background story will be this field-induced post-condensation. And the interesting aspect there is then if you go to reduced dimensions, what would you get in this situation? Let me start now with a general framework. I've been really working extensively on systems where we have very exciting small units of quantum nature, and these are simple dimers. So in quite many materials now, you find structurally the formation of pairs, and this is one of the classic model materials here. In this case, the magnetism comes from copper 2+ ions. They are a pair of these antiferromagnetic exchange, which is dominant. So the spin signets, but they are not isolated. That would be pretty boring. They are interacting in a network. And then this network can be 1-dimensional, 2-dimensional, 3-dimensional, and that's very nice. And because this basic ULIC is essentially a natural boson where the ground state is singlet, you make an excitation, you create a triplet. This is a very versatile platform to do exciting physics. We used that in the early 2000s to demonstrate one of the early quantum critical points, one where basically people really understood what the 2 phases on both sides are. In this case, you apply a strong magnetic field to this particular material, you get Zeeman splitting of these triplet modes, and then eventually at the critical field, you get this field-induced critical point and the state with long-range magnetic order, which was then mapped onto both gases and then condensation phenomena. So this is very, as I said, quite a versatile framework. There are really many materials. I'll come back to that later. The general thing you need to know about this is really that there is these dimers. I showed to you a bit this before. The ground is a singlet, the excitation is a triplet. There are 3 of these guys. If you map the spin system onto effective boson model, you get such type of Hamiltonian. So the important parameter are the hopping for these particles on the lattice. And then you have an interaction term and you have a chemical potential, which you can control with a magnetic field. And here on the right, you see again the picture, how you go from a spin model to a lattice boson model. And again, depending on the material, these pieces can hop around in 1D chains, 2D planes, 3-dimensional structures, can have frustration like the Shasky-Sutherland you heard about yesterday. How you control it then in experimental materials is simply that you can have different T terms and JC terms depending on the material, and you can also control these parameters by pressure. So these are the exciting phase diagrams. I'll come back to these later. So in general, if you're interested in the mapping and what you can do with it, how it compares to cold atoms, you could read an article by Jerry, myself, and Oleg in Nature Physics more than 10 years ago comparing this, or this book chapter with Corina Kollat in this Universal Themes of BEC, where we do the comparison between different systems. There are now really many materials where this framework has been used over, let's say, more than 10 years now. There's a good review of modern physics. You see a summary here. That's some of the phase diagrams. On the left, you see temperature. It's all down to a few Kelvin, not nanokelvin or so for cold gases. On the x-axis is the magnetic field. You have to apply 5 Tesla, 10 Tesla, 30 Tesla, depending on the material, to close that spin gap and get this field-induced BEC phase. The framework also can apply to dimers with spin 1/2, dimers with larger spin. It can be in a Haldane situation where you have a gap because of Haldane. It can even be for large D system, basically where the gap is done by anisotropy. Now what is quite interesting is of course to play around with this, apply pressure, field, study these different systems. But it's really also, there are more fundamental questions, and that could be, what happens with dimensional effects. Obviously BEC is a condensation and ordering phenomena. We all know that this can only happen at finite temperature for 3D systems. You want to know then what happens in 2D, eventually in 1D, and how the things go across these things. You could also talk about the disorder in the bosons, and I could quickly mention this. Frustration is important, out of equilibrium is very exciting. And finally, we could also think to do the same thing and go across a metal insulator transition as well, where the charge gap comes down in a system. And so there is an entire framework there. I will show you now 2 classes of materials. As I said, first is this very one-dimensional case. These are metal organic materials. You see the magnetism is from copper. There is this organic guy which essentially isolates these one-dimensional units. You see on the right some of the crystals, then can be grown in powders, but also very large single crystals. This dimension here will be nearly 2 centimeters. So you see there are beautiful pieces. These are very, very, very good one-dimensional magnets. And then the big breakthrough at that time really was the computational push, that is a DMRG 1D, perfect. So here you see the calculation of the full dynamic structure factor done by Thierry and collaborators using DMRG around 8-9 years ago. On the right, you see the 1 magnon spectrum if you do one of these triplet excitation. On the left, you see the 2 magnon spectrum if you do 2 of these guys at the same time. Then you can form a bound state, which you basically see here below the 2-particle continuum. And this bow tie is the 2-particle continuum. You also see more on this. You see that, for example, the relative strength of these different contributions. And I said that's very important because with the neutron spectrometers we have now, we can measure these signals on an absolute scale. So, if you say that this is 10 times weaker than the rest, you can measure this on an absolute scale as long as you know what the weight of your crystal is. That's now exactly what we did in this material. You see an example here. Top left is the experimental data, and then you see the DMRG calculation, and that's, the physics result there. The 1 triple excitation for a ladder has been known for a while, but what you see here is also full, it's not just the energies, it's also the intensities that are right, the full structure factor. On the bottom left, you see some of these intensity plots as a function of momentum. Also there we have fully quantitative agreement. You can check how one-dimensional the system is by cutting the data in a different direction perpendicular to the chains of the 2. You see on the top right panel that this is a very 1D system. And what you do then, you extract the exchange parameters you see here for the 2 materials. And these you get now on really very high precision. You see that's millivolt scale here. The errors are very small. And once you have fixed these parameters, and in this situation here where we understand what the excitation is supposed to be, these are fixed. You see, you know your system very, very precisely. You can even zoom in and spend another 2 years figuring out exactly the anisotropy parameters on 1% level if that's what you need to benchmark your theory. So this is quite powerful now. So we have a system where we have basically, we have put down all the parameters, we fix these, and then we can do both complicated experiments with field and pressure, and we do computational work and can then benchmark these results. This what you have done then is we calculate the 2 magnum cross section and the bound states, and then you can just zoom in a different region of the reciprocal space and analyze exactly these quantities in the data. And here you see the same type of figures. On the left, the data. This lower edge is a bit of the leakage of the one triplet cross section. Here is then the 2 triplet bound states, and you can again quantitatively describe the weight of these spectra, which can be very powerful. If you apply now a magnetic field, as I mentioned in the beginning, there is this field-induced critical points, and then the question is what happens in 1D systems, and I showed you before that the system here is actually extremely 1D, and this is the generic phase diagram in such a case. You get a quantum disordered phase, quantum critical points, and then this BEC phenomena is replaced by a spin lattice liquid, and Thierry is going to talk more about this. So here there's thermodynamic measurements to identify this phase. There's no long-range order here, but you see a crossover. But then eventually, of course, you tell yourself that, okay, there's nothing like a real 1D system. And indeed, it's true. There's a very, very weak interaction here between these chains. So if you cool down the system to 100 millikelvin in this situation, go down to this box, you indeed find again the BC physics. And Thierry will explain to you how you still see the one-dimensional correlations in these systems. So what we have done together recently is now to mix up the chemical composition in this a bit. And you see here some examples. The top are powders now measuring bromine and chlorine. And then what you do, then you continuously tune the exchange parameters. You introduce disorder. It's quite complicated to really characterize what's happening when you chemically dope, because you also distort local symmetries. But then what you are interested in is, of course, to search for exotic phases like the Bose classes and so on. And then see the competition between localization, basically, disorder in general in these systems. There we have also a theoretical framework where we can benchmark the results. So we are working on this right now. I will now go back to this slide. So I showed you examples where essentially you go from 1D, you have a nice material, you can use these new spectrometers, you get full 4D information, you can cut the data and compare in a quantitative way with your DMRG calculations. Now, if that was an interesting case for 1D, that's simple to measure, exactly good to calculate. So this is the perfect situation. Eventually, if you cool down in low temperature, you also still see the condensation phenomena, the 3D effect, and then lattice liquid and stem cell. What is quite interesting is actually to go to 2D and ask yourself if then maybe you can pick up some of the Kosterlitz-Taurus type physics. So, if I just stay with the dimensionality and not continue with the disorder question too much here, I have now a quite exciting example about the 2D system where basically you can see what you get in this case. This material is somehow a classic. It's actually a pigment from China. It's called Han Purple. It was used at that time to color, for example, the terracotta warriors. You see the beautiful examples here. Nowadays, of course, they have lost all the color. How they did this, they took the pigments, which they basically did in a ceramic furnace, very high temperature, and then you mix it with egg white. And then the paste you get, you put to color things. And of course, the egg white will not last for 2,000 years or more. So that's essentially why all the colors came off. The material structure you see here, you see my old friend again. That's the copper dimers here. They fell on very two-dimensional sheets. That's very exciting. So people studied the phase diagram of this material in the group of Ian Fisher some years ago, and here you see this high field data. It's beautiful data, very low temperatures, few Kelvin, that they measured out to 50 millikelvin or below at very high magnetic fields at the National High Magnetic Field Laboratory in Tallahassee. And that's what you see what they found. So they found a very exciting phenomena. So it looked like the dimensionality of the system would actually change from 3D to 2D once you go to a critical point. And that's a very disturbing thing, because normally we go to lower temperatures, and the example before I just showed you that eventually low temperature things start to couple because there's a very low energy exchange parameters making the system 3D. And obviously here the opposite happens. You cool down and the system loses the dimension, goes from 3 to 2 rather than from 3 to stay 3 or being 2 and then go to 3. So this was a bit surprising. And so there were several scenarios were discussed over the years. One was that, that these layers are fully decoupled. We know it doesn't exist in nature. It said that frustration was a potential mechanism. It's in principle still is possible, but there is arguments why it's a bit unlikely to really lead to full decoupling because of virtual hopping processes. Then we also found a structural phase transition, and we also said that it has to be important that you have different types of layers, A, B, and C. And then really a big shock came. So normally we do understand if something is a ferromagnet or an antiferromagnet or so. But in that particular case, you will figure out that this was not the case. So here, ab initio calculation showed that actually the exchange in the dimer should be antiferromagnetic, but those between the dimers should be ferromagnetic. And that was a big surprise. 5 minutes, yeah, I got you. Yeah, okay, thank you very much. So there was an ab initio story saying that, okay, maybe the exchange is ferromagnetic, which basically renders all of these discussions here on top, all these papers kind of a bit in a different category. And so, okay, we went out to say, okay, we have to do a better job on the Hamiltonian. And just before I advertised, we can now do everything with these spectrometers. You map everything, you simulate everything, and you get it. So we took one of these spectrometers, this old crystal, and that's what we did. And the data you see here now that you are maybe more used to when you do ARPES or so. So you do the full band structure of a thing in all Q directions. And here, that's exactly what you did. On top left, you see the different bands of these triplet modes. You see 3 modes because of these different layers. And on the bottom, you see again a calculation, in this case using RPA to basically simulate the spectrum. Then the first situation here, where you basically start with the initial scenario of all alpha antiferromagnetic exchange, you see there's little matching between the two things. Then you make everything antiferromagnetic. It kind of looks better, but the phase, the zones are not correct. You flip the signs of some things. You basically get the splitting at the right time, still the wrong zone. And then eventually, if you make everything fit, you get a very good matching. The differences can be very, very subtle. Now the question if something is a ferromagnet or an antiferromagnet, in this case, you just focus quickly on this panel here. I don't know if you can see it in my mouse, it's C and G panel. So you see there's a very weak splitting in intensity. And basically if you just change, if you just change the sign there, there's only a very kind of subtle change in the intensities. So you really have a very good spectrometer, very good data to be able to see these subtle things. So anyway, we did that, and we extract exchange parameters. As I said, once you have the right model, the right symmetry, you understand the crystal structure, which sometimes can be dangerous if you don't, you can then pin down these exchange parameters very precisely. And now another success of comparing, let's say, experiments with theory. So we took these exchange parameters, and you see they are very, very precise. The system is extremely layered. Basically, it's very 2D. And we put this in this case because it's a ferromagnet. In this critical parameter, there's no frustration in the system. You plug this into quantum Monte Carlo, and you see basically here the result. And this is just simply beautiful, I found. So this is basically a very high precision experimental work with torque and so on the phase diagram. At the bottom, you see quantum Monte Carlo. And again, there's essentially no free parameter here. And it's a very, very layered systems. And of course, you know that how strongly we depend on exactly the parameter size of the interlayer exchange. And this case, we get very good comparison. So now we fully understand why actually something changes and looks like 2D. But unfortunately, this system here is not 2D. It's just a consequence from different types of layers, which basically both talk to each other. So there's unfortunately nothing universal about this type of phase boundary we can see here. But we fully understand the effect. When you're interested, you can read the full story in this article on the archive. Now we'll close the loop, go back to the FEL. So I said now we can do a lot now, doing experiments, computational work in equilibrium. And at the beginning I said this new machine now will allow us essentially to do time-resolved studies. And why should this be very exciting? And I'll show you this, and that's what we are working on right now. Top left, you will see, again, this generic phase diagram of a quantum critical point. So what we want to do now is basically do this in a dynamic way. So what you do is you position yourself somewhere close to the critical phase boundary here, And then you can do a couple of very beautiful experiments. One thing is to hit some phonon modes, which change the exchange parameters. And then you shoot the system at very low temperature into an ordered phase, and eventually it comes back. You can also do oscillation things. You can do quantum quenches with field pulses and things like that. So we're now looking into this. And here again, I think what the really potential is on quantum magnets is that initially we start with a very, very well-defined Hamiltonian. So it's not a cuprate where we still fight over what it really is. So it's something we really understand. It's a Heisenberg Hamiltonian with a J. And we can then say, okay, now let's change this J 30% in 10 picoseconds or in 10 femtoseconds. And we can ask ourselves, what does it do? You know, does the gap collapses? How quickly does it come back? And so this is what we're working on right now. So I would like to finish now. I thank, of course, my students, postdocs that have been working both on samples and also on experiments. And of course, there are very fruitful collaborations with quite a few theory groups here in Europe, mostly now. So that's with Thierry, who will continue the topic right now, Corina Collat in Bonn, also Frederick Millia at EPFL, Nicolas Florency, Bruce Normand, Andreas Leuchli, Kai Schmidt. So this has been a very close and that's very fruitful in the sense that both now understand a bit better after a while, you know, what is important in experiments, what's important in the theory. With this, I would like to finish. I think I showed you on the experimental side that we have now quite cool new spectrometers which can give very detailed information about correlation functions of all different sorts. And the examples were on quasi one-dimensional, quasi two-dimensional lattices. That's basically to see what happens to this magnon BC when you go from 3D to 2D and also eventually to 1D, very thin spanning Lagrangian liquid physics. And now we are working on disorder and so on. And then the really new thing, I believe, is to work on disorder out of equilibrium effects using the Hamiltonians we understand very well and go into the time dependence and see what we'll find there. Okay, thank you very much. I think I'm through with my time and thank you for your attention.
Christian, and we can take questions now. I will try to repeat them so that you can actually hear them.
It's kind of simple. What timescales do you hope to access with the electron laser?
Okay, the question was, what timescales do you hope to access with the free electron laser? No, I have to speak here. Sorry. Christian, what timescales do you hope to access with the free electron laser? Good.
Yes, thank you very much. Yeah, it worked very well with the microphone like that. Yes, so typical pulses we get from the FEL are you know, in the region of femtoseconds, you know, and the resolution we get is 10 femtoseconds, something like that, if everything goes well, maybe sometimes only a 100. But people are already now working on much shorter pulses even. So this is basically, so things are matched to sometimes terahertz type of phenomena. So in terms of the pumps we have, or the perturbation, you can go for both things. You can make pumps of some time scale and then see relaxation phenomena, but you can also hope to do interlock type systems where you basically have oscillations and just dissipation is a problem.
Perhaps a quick follow-up on that question. What what amount of parameter changes do you hope to access? I mean, when you say you want to move in the phase diagram in the time-dependent fashion, you mentioned, I think at 1.30% of some interaction parameter, but kind of, is this the typical scale you expect?
It depends. I mean, basically, you have to hit the phonon in this case. That makes a move of an atom, which changes the J in this case. And then it really depends on, you know, how lucky you are. And so typical changes of the J's, you know, which I achieved with pressure in materials, was you know, few percent can be enough to actually go across the quantum critical point. It really depends on the system, and having a few percent change is very realistic with this approach. You don't need 50% or 100%. I mean, many of the materials we study now, they are already, let's say, a bit fine-tuned. They are close to critical points, and then you just have to pay by having to have very low temperatures to still do the experiments. But we are already, you know, looking for systems that are quite close to criticality, so you just need to.
Let me see, further questions in the audience. No one wants to, yeah, very good. Okay, the question is, what is the origin of the disorder and can you tune it?
Yes, it's just done by chemistry, so I don't have go back to the initial structure picture. So here you see that the exchange, this is a copper, this is a copper. Can you see my mouse?
Yes.
Yeah.
Okay, so these two, and then the super exchange, which goes through these halide ions, you see, these the blue guys here. If you replace bromine by chlorine, there's a distribution of these atoms going here on these blue sides, and then they model the super exchange. So what you get is, in this case, in first approximation is that locally the dimer bond in a leather has a different value than in the rest of the bulk of the system. But it's kind of to fully characterize it, it can be challenging because there's also distortions of the geometry. There might be some preferred sites where these atoms go. So it's not as simple as just, you know, kind of replacing two atoms and changing the electronics or doing the doping or the lattice parameter. It's more local effects. That's why it needs a bit more characteristic.
Okay, very good. Well, I see at the moment no further questions. Christian, thanks for joining us in this way. I think it worked very well.